All right, welcome back. This is video 16B. In video 16A, Joe Cooper-Shannon introduced us to the concept of hypothesis testing with a proportion problem. In this video, we're going to go through some of the general steps. So this lesson, for the most part, will highlight proportions. However, the steps for hypothesis testing, whether it's proportion or means, whether you have one sample or two sample, in general, they're pretty much the same. So in statistics, we'll run many types of hypothesis tests depending on if our variable is categorical or quantitative, and depending on if we're investigating one or two samples. The previous example we looked at, we just had one sample, but in the future we'll look at problems with two. You can always follow this model to make sure that you hit all of the different steps, and the details will change slightly depending on what kind of variable you have and how many samples you have. But in general, the steps for running any hypothesis test. Number one, you want to read and understand the context of the problem. Maybe read the problem a couple of times. Determine if the variable is a categorical variable or a quantitative variable. And are you working with means or proportions? If your variable is categorical, you'll be working with proportions. When it's quantitative, you'll be working with means. And then, do you have one sample or do you have two? After you understand the content of the problem, go ahead and write down your two hypotheses, and then you'll check the appropriate conditions before proceeding. The conditions, again, will depend on which type of problem you're looking at, but you'll still want to write down if the conditions that need to be met and if they have indeed been satisfied. All right, number four, based on the collected sample data, we'll convert sample proportions or sample means to a test statistic. So we'll compute a test statistic. The formula for that will change depending on the type of problem. And then number five, we'll determine the probability that you get the test statistic that you got, or one that's even more unusual, under the assumption that that null hypothesis is correct. This probability is something called a p-value. We're going to give you more information about this today. This is really a big key in our hypothesis testing. All right, then based on that p-value, if the p-value is small, then you'll reject the null hypothesis. You'll find evidence in favor of the alternative. And then besides just saying we reject the null hypothesis, the last step in hypothesis testing, which is really important, is what does that mean? You know, I reject the null hypothesis, but what does that tell me about the percentage of CECL students who are smokers, or the average number of credits a student's taking? So write a concluding remark in the context of the problem. Don't stop with, we reject the null hypothesis. Okay, so those are the steps sort of in general. In this lesson, we've been looking at proportions. So let's go through the steps. If we're looking at a one proportion z-test. One proportion, we just mean we're looking at one sample. It's called a z-test because eventually when I write down the formula for the test statistic, you'll notice that it's going to be a z-test statistic. So the first thing we'll do is we'll write down our two hypotheses. Remember, the null hypothesis is what you're going to assume is true until you find evidence based on your sample in favor of the alternative. So in general, what the null hypothesis looks like, we write an H with a subscript of 0 to denote the null hypothesis. This is a proportion problem, just one proportion. So we want to know, is the population proportion equal to some figure? I'll call this number P sub 0. So P sub 0 here is just a number. If we read an article that 20% of people are smokers, this would be 20% or 0.20. The alternative hypothesis is what you want to test. This is sort of your claim. And so for alternative, we write H with a subscript of A. And what your alternative hypothesis is will depend on the wording of the problem. Do you want to test that the proportion is less than this hypothesized value? If that's the case, then we would say that P is less than P sub 0. You could test that it's more than that value, or just that it's different from that value. So it'll be one of these, not all three of them, and which one you choose will be based on the context of the problem. So read the problem. So this will comes from the problem. Comes from the context of the problem. All right, the next thing we'll do after we have our hypotheses set up is we'll go ahead and check the conditions for hypothesis testing. And so the conditions for hypothesis testing, if these are met, then we'll be able to use the normal model. When we're looking at proportions, we have to have a variable that's categorical. You know, you either smoke or you don't. Our sample should be one that's a random sample. If it's not a random sample, it should at least be unbiased. If this assumption's not met, then pretty much everything else you do doesn't make any sense at all. So that's a very important one. Your sample size needs to be less than 10% of the population size. And then we have that success-failure condition. We want to be expecting at least 10 successes and at least 10 failures. So if we're looking at a sample of Cecil students and it's a smoking problem, at least 10 smokers, at least 10 non-smokers. How we can check that, if you take your sample size and multiply by that hypothesized proportion, that p sub 0 from your null hypothesis, that should be at least 10. And then for the failures, n times 1 minus p sub 0 should be at least 10. So next thing we'll do is we'll go ahead and check those conditions. Once we've checked those conditions and we know that we can use the normal model, we're ready to run our hypothesis test. And so to run our hypothesis test, we need to compute a test statistic. So we'll look at that next. All right, and for a proportion problem, the test statistic that we'll look at is a z-test statistic. And you're going to take your sample proportion. What did you get in your sample? You're going to compare that to the hypothesized proportion from the null hypothesis. We're going to see how far off they are. And we're going to talk about that in terms of the standard deviation. So we divide by the standard deviation. Remember z-scores were like take an observation, subtract off the mean, divide by the standard deviation. This is kind of the same thing, but for a proportion problem. All right, and then based on this test statistic, we're going to make a conclusion. This is a z-test statistic. You know that z-scores are centered at 0, have a standard deviation at 1. We know what kind of z-scores are fairly common. We know what kind of z-scores are very unusual. So we're going to see if we get a z-score that's pretty common, a sample proportion that might happen pretty frequently, or did we get a z-score that's pretty unusual? And so how we look at that z-score is we're going to use this z-score to find the p-value. And so what we'll do, we're going to draw a standard normal curve, draw a z-curve here. So this is z. 0 would be in the middle. And you're going to take your test statistic that you just computed. I'm just going to put this somewhere. Let's say it's here. And you're going to shade the area under the normal curve in the direction of your alternative hypothesis. If the alternative hypothesis had said that p is greater than a value, then I would take my normal curve and I'd shade greater than. Had it said less than, I'd be shading the area to the left. We'll talk in a later video about what happens if it's not equal to. But that area right there, that's the likelihood of getting your test statistic or your sample proportion or one even more extreme. And that's what the p-value is. So this was an example for a greater than test, just to make a note. You know, had it been less than, we'd shade the area to the left. And this area right here is the p-value. It's the probability of getting data like ours or even more extreme if that null hypothesis is true. Ours or more extreme. Okay, and we're going to base our conclusion about our hypothesis test on that p-value. How likely are you to get sample data like you observed or even more extreme if the null hypothesis is true? If you're not very likely to get that kind of data, then that makes you kind of wonder, maybe this null hypothesis is not true. If you're fairly likely to get that, then okay, we continue to believe the null hypothesis. All right, so the last two, kind of talked through. Make your decision if your p-value is small, if this area here is small, we're not very likely to get that kind of data, then we reject the null hypothesis and find favor for the alternative. Whereas if your p-value is large, then we fail to reject. We keep the null hypothesis. We continue to believe that. And then the last thing we'll do, again, we'll write a concluding remark based on your decision in the context of the problem. Don't just simply end with we reject or fail to reject the null hypothesis. Okay. You'll also notice that some of the language is a little strange. You know, we reject the null hypothesis. We fail to reject the null hypothesis. Why can't we just say we went with one or the other? I think we'll address that here in a future slide. So that is intentional. Okay. Next slide. Let's talk some more about the p-value and the logic of hypothesis testing. So here's the fundamental question behind every hypothesis test. You want to know, you've collected this sample data. Are my data surprising if that null hypothesis is true? When your data are surprising, that's when we reject the null hypothesis and we find evidence in favor of the alternative. The probability of seeing data, sample data like ours, if the null hypothesis is true, that is the p-value. And the smaller your p-value gets, the more unlikely you are to observe that kind of sample data given the null hypothesis is true. So the more likely it is that the alternative is the correct hypothesis. So the smaller your p-value, the more likely it is that the alternative is the correct hypothesis, not the null hypothesis. All right, a couple other things about that p-value. Okay, we said when it's small. How small? Keep in mind what probabilities are. They're areas under the normal curve. They're probabilities. So they're probabilities. A p-value will always range somewhere between 0 and 1. And you know what would be defined as a small p-value? Oops, that's not what's written here first, sorry. In almost all cases, if you have a p-value of say 10%, 0.10 or above, that's not showing much evidence in favor of the alternative. That means that you could get sample data like you did 10% of the time. 10% of the time, 1 out of every 10 times you collect a sample, you would get sample data like that. That's not extremely unusual there. So in almost all cases, if we have a p-value that ends up being 0.10 or above, we don't find much evidence in favor of the alternative. Next bullet point. The collected data are plausible under the assumption that the null hypothesis is true. And so if that's the case, then we would fail to reject the null hypothesis. And this is when we have a p-value here that's not very small. Trying to see if this is where I say it or later on. I'll say it here too. When we fail to reject the null hypothesis, we're not proving that the null hypothesis is true, we're simply not finding enough evidence to the contrary. So that's sort of an important difference. We never say we accept the null hypothesis or we prove the null hypothesis. We just sort of fail to get rid of it. It was our initial assumption. We sort of keep that. All right, a couple more. In almost all cases, if you have a p-value that's below, that's 1% or below, 0.01 or below, that's showing pretty strong evidence in favor of the alternative hypothesis. This means you're only going to get sample data like yours 1% of the time or even less than 1% of the time if that null hypothesis is true. You know, how likely is it to get a sample where those results would only happen 1% or sometimes even less than 1% of the time? That doesn't seem very likely. So therefore, almost always we'll find evidence in favor of the alternative hypothesis. So the collected data are not plausible under the assumption that the null hypothesis is true. And when this happens, we reject the null hypothesis and find favor for the alternative. So we would reject the null hypothesis. And then you'll notice we said above 10%, okay, that's pretty believable. Below 1%, that's not very believable. What if you're like in between 10% and 1%? What's our decision there? And that's where it's not always as easy. So let's draw a picture of p-values. All right, so I'm going to draw a number line. At some point I'll make a break. So p-values range from 0 up through 1. So these are p-values. And let's plot here some different p-values. Let's go 0.1, 0.2, 0.05, about 0.01. So some different potential p-values you might get. Really, you could get any number up here on this number line. But let's talk about what some of them show. And I'm going to write this in terms of how much evidence is that p-value showing in support of the alternative hypothesis. All right, so let's start with some easy ones. If you get a p-value that's up here, somewhere between 20% and 100%, you know, you get sample data. The likelihood of getting that sample data under the condition that the null hypothesis is true is like 20%, 30%, 40%. Okay, that happens pretty frequently, excuse me. That doesn't seem like that's unusual at all. This is showing absolutely no evidence in favor of the alternative. So here there's no evidence. When you dip below 20%, you know, really we said above 10%, there's no evidence. I guess you could say if something only happens 10% of the time, 11, 12% of the time, whatever, perhaps there's very weak evidence in favor of the alternative. Most of the time we will not find favor for the alternative hypothesis here, but you know, those probabilities are smaller than they are for larger p-values here, so we could say that this is very weak evidence in favor of the alternative. All right, once you go below 10%, now we're finding some more evidence in favor of the alternative. We said that if you're below 1%, that's some pretty strong evidence in favor of the alternative. So I'll switch to down here. This is some pretty overwhelming evidence. This area, kind of the gray area. You know, one person might interpret this one way, somebody else might interpret this slightly different. But typically, if we have a p-value, get sample data, and the likelihood of that happening is 5% or less, this is still pretty strong evidence that that's sort of an unusual thing. We don't think that that's very likely. This is probably some strong evidence in favor of the alternative. Whereas if it's 5 to 10%, 0.05 to 0.10, that's more moderate. The 0.05 though, I mean, this is where we drew this on this number line. It's not like when you magically cross over that, all of a sudden your evidence is more moderate, and here it's, you know, if you're smaller than that, it's stronger. It's just a number on a number line. The smaller that your p-value is, the stronger the evidence in favor of the alternative, and the bigger that p-value is, the less evidence that's in favor. But you know, this 0.05 for some reason sometimes tends to be sort of a cutoff that we'll look at. But again, none of these are any magical numbers here. Keep in mind the context of what a p-value is. The p-value is, you were trying to test this hypothesis, you had a hypothesized proportion value, you collected sample data, in your sample you got a sample proportion. How likely are you to get that kind of sample proportion if the null hypothesis is true? If you're very likely to get that kind of sample proportion, then okay, we keep the null hypothesis, we don't find in favor of the alternative. If you're unlikely to get that, and the more unlikely you are, the stronger the evidence in favor of the alternative. So p-values are really critical to hypothesis testing. We'll talk about them a lot. If you have questions about the p-value, please make sure that you talk to your instructor in class. In the upcoming videos, we'll apply all this, run through a few problems, and we'll always talk about interpreting that p-value. So I think that's the end of.
Put the fail to reject underneath it.
Did I not? Oh, I did do that. Thank you. I'm like looking to see what I forgot. I talked about that this is evidence in favor of the alternative, but I didn't write what your conclusion would be. Thank you. So let's write that. When you're down here, if you're finding evidence in favor of the alternative, you would reject the null hypothesis. So down here, we would reject. If we're up here, we're going to fail to reject. And maybe I'll even say like above 10%, we're going to fail to reject. And then I talked about how this wasn't like a magical number, but I didn't write my conclusion down here. You know, what would you do in here when it's kind of like that moderate evidence? That's like a gray area. Some people might reject, some people might fail to reject. Sometimes it'll depend on the consequences of the problem. So in here, this is more of a gray area. And really, sometimes problems can go either way when they're here. But smaller p-values will reject. Larger p-values will fail to reject, and there is some gray area in the middle. Thanks. Okay, now I think I'm completely done with this, although I said this earlier, make sure you look at that note. If you do not reject the null hypothesis, you have not proven that the null hypothesis is true. You just didn't have enough evidence to get rid of it. So, okay, thanks for watching.